This presentation is about Laplace transform and its inverse transform, and this is 홍성우 and
서민준.
to explain about it. First, this is index of the presentation. We'll talk about Laplace transform's property and prove its inverse transform by using complex analysis theorem. At last, as Laplace transform is generally used to solve differential equation, we applied it to a self-made mathematical model and got a differential equation solution. This is our presentation's abstract. This equation is Fourier transform, Laplace transform, and inverse Laplace transform, and these are our presentation's main points. These are properties of Laplace transform. As we know the form of Laplace transform, these can be easily proved by integration by parts. If you know the form of Fourier transform, you would feel familiarity from Laplace transform, because Laplace transform is a generalized shape of Fourier transform. In other words, Fourier transform is a subset of a Laplace transform. This is Fourier transform. It's usually used to analyze signals. It changes functions domain from time to frequency. We can easily understand it by using complex plane. We can think the function inside the integral as polar coordinate. Radius will be ft and the argument will be exponential minus 2 pi I ct, and the integral's value would be the product of centroid of the complex function and the duration of the function. But Fourier transform has a limit. It can't transform a diverging function because as Fourier transform's domain is real number, the multiplied function's power is purely imaginary number. So it doesn't converge to zero. But in real life, we should have to analyze diverging function too. Due to this point, we use Laplace transform. Laplace transform's domain is complex number. Now we can make diverging function converge to zero. It's used to analyze system, usually at electronomics, or solve a differential equation. Now let's see both transform in ones. They look very similar and they also do a similar role. Now we know about Laplace transform, I'm going to explain about inverse transform. Before to explain it, basic understanding about complex analysis and inverse Fourier transform should be followed. I'll use these four theorems to explain inverse transform. First, this is Cauchy integral formula. It shows if function is analytic in some range, its values by contour integration, and from this theorem we can derive Cauchy's integral theorem. And it means if there's no singularity inside the closed integral's contour, its value equals to zero. And this is Laurent series. It's an expanded version of Taylor series. We need to know this series because we need minus power at inverse transform. We will concentrate on the situation when n equals minus 1. This is the final goal for previous theorem and it's the key to do the inverse transform. If you do the closed integral that its contour includes singularity, its value can be found by using residue theorem. This is because when function is expanded to Laurent series, its integral value equals to 0 except when n equals minus 1. By this, we will find a minus 1 and easily get the integral value. Next, this is Jordan's lemma. It can be used when function is on a decay condition As the half-circle contour's integral value converges to 0, the closed integral's value equals to the linear integral's value. We now have essential complex analysis theorems. We can talk about Bromwich integral. This is the form of inverse Laplace transform. The sigma value will be set to include all singularity in the contour. It's a linear integral, but due to Jordan's lemma, we can calculate it by using closed integral. We do the inverse transform by using residue theorem, and the inverse transform can be proved by using inverse Fourier transform.
Next, we have the transformation table. The previously explained method involves a very complex integration process and requires an understanding of complex analysis, so generally, commonly used functions can be easily found using the Laplace transform table. Instead of driving them each time, it is more convenient to memorize and use them directly. In the following table, the left side shows the original function and the right side shows the function after applying the Laplace transform. For example, when transforming exponential of at, it becomes 1 over s minus a. Using this table, given differential equations can be easily transformed. Now, we will look at actual examples of differential equations and see how to apply the Laplace transform and derive solutions based on it. First example, we will solve the following differential equation with given initial conditions using the Laplace transform. Applying the Laplace transform to both sides results in the equation s times y of s minus y of 0 plus 2y of s equals 1 over s. Substituting the initial condition y of 0 equals 0 and simplifying, we obtain y of s equals 1 over s times s plus 2. We decompose this into partial fractions, and by applying the inverse transform to each term, we can derive the solution to the differential equation, which is 1/2 minus 1/2 times exponential minus 2t. And second example, we will solve the following differential equation with given initial conditions using the same method. Similarly, we apply the Laplace transform, substitute the initial conditions y of 0 equals 1 and simplify to obtain an equation. And decomposing this equation into partial fractions, and then applying the inverse transform, we obtain the solution exponential 2t. Last, final example. Similarly, after applying the Laplace transform, we rearrange the equation and express it using partial fractions. By applying the inverse transform, we derive the solution 1/3 times sine t minus 1/6 times sine 2t plus cosine 2t. The three examples above respectively illustrate differential equations composed of polynomial functions, including exponential functions, and including trigonometric functions. These examples demonstrate that the Laplace transform makes it easier to solve complex differential equations. Next, we will explore how to solve practically used differential equations using the Laplace transform and apply them directly. The model used in this study is the two-compartment model. This model assumes that a drug is distributed between two compartments and moves between them. It is used to describe the change in drug concentration over time in more detail and is represented by the following differential equations. dC1 dt equals minus K1C1 minus K2C1 and dC2 dt equals K2C1 minus K3C2. Here, C1 represents the concentration in the central compartment, C2 represents the concentration in the peripheral compartment, and K1, K2, K3 are the drug transfer constants. The total concentration C of T is the sum of the concentration in both compartments. To obtain each concentration, we first solve the first differential equation. Applying the Laplace transform to both sides and simplifying, we derive an equation. By taking the inverse transform, we obtain the expression for the concentration in the central compartment, C1 of 0 times e to the power of negative k1 plus k2t. To solve the second differential equation, we apply the Laplace transform to both sides and simplify, leading to another equation. Substituting the previously obtained expression, we rewrite it as follows. By separating it into two terms and applying the inverse transform to each, we derive the expression for the concentration in the peripheral compartment. Here, since the first term gradually decreases in influence over time, we can approximate the solution using only the second term, simplifying the modeling process. Thus, the concentration in the peripheral compartment, C2 of 0 times e to the power of negative k3t. By adding these two concentrations, we can define the differential equation for the two compartments model. Using the obtained differential equation, we analyzed actual blood drug concentration data. The data was sourced from the Convergence AI Institute for Drug Discovery. The study was conducted in Google Colab with time values ranging from 0 to 24 hours, and the corresponding drug concentration data was input for analysis. The constants K1, K2, K3 were obtained through regression analysis to determine the optimal values. The modeling results are as follows. While there are some differences from the actual data, the model shows a fairly similar trend. Thank you for listening to our presentation.